to call Dr. Mubashar Ali from Poland.
Hi, can you hear me?
Yes, please. Yes, please. Share your PPT.
Can you see my screen?
Yes, please.
So, my name my name is Mubashir Ali, and I am PhD scholar at Wrocław University of Science and Technology, Poland. Today, my presentation topic is computational evaluation of perovskite-based metal catalysis for methanol electrooxidation. So this is the table of content. So we will follow this. First of all, introduction, then computation design, and after that we will discuss some results, and then we will draw a conclusion. So, so first of all, due to the growing global energy demand and increasing the sustainability challenges, so researchers are focusing to find some low energy emission and energy technologies for renewable and safe environment. So the direct methanol fuel cell are the attractive because we only use the liquid methanol, which is easy to store and transport to produce the electricity. Their performance is mainly depend on the methanol oxidation reaction, which is the main part of the direct methanol fuel cell. Uh, in this process, the metal sport interaction are very important because this sport can change how the metal catalysis behave and affect how the reaction steps occur and how the efficiently catalyst will work. So we will discuss in detail. So first of all, we will discuss about the electrocatalysis process. This is the equation for the methanol oxidation. Half reaction can, in which we can see here that this is 6H positive and 6 inactive. It means during the each 6 steps, one electron and one proton are transferred to the electrode and the solvent respectively. So it has to be stressed that we need a specific amount of water to require to process and the water molecule undergo the splitting as similar to the OER reaction. So the main difference between the OER and the electro oxidation of methanol is there is no oxygen to oxygen bond. Here only the carbon to oxygen bond will be formed. So this is the schematic diagram which presents a complete reaction pathway or network for the methanol oxidation reaction of any perovskite system. So it shows that all the chemical possibilities and surface intermediates, for example, CH3OH to CH2OH, CHOH. These are the all possible configurations for the terminations of the perovskites or other MXene layers. So this each box represent the adsorbent intermediates, and these different colors of arrows distinguish the sources of the removal hydrogen. For example, these red arrows represent the carbon hydrogen dissociation, and this blue arrow uh, represents and these blue arrows represent the oxygen hydrogen dissociation, and the green arrows represent the hydrogen which coming from the water splitting. By mapping every possible pathway including the alternatives such as CO uh, CO and OH versus the carboxyl group, which is COH and COOH. This is the full mechanism explored using the computational simulations and the which predicts the thermodynamical preferred reaction pathway for and date step elimination for the electrocatalysis. So this is the energy profile for the TiO2 terminated SR services, which compare how the reaction energies changes with the applied potential. These blue lines represented the reaction at zero applied potential, while this pink line correspond to the thermodynamic reaction potential, and these green lines represents the minimal external potential required to make all the step downhill. So the profile reveals that the methanol first undergoes the carbon hydrogen bonding, and after that it will go from CH3OH to CH2OH and further, and at the last CO2 will be produced. So the main point is that at the CO2 react with the water with the OH hydroxyl group to form the carboxyl, which is COOH intermediate before releasing this carbon dioxide. The limiting step um, is that which involve the water dissociation and define the overall potential, which is we calculated is around 0.56 electron volt. We can see here from that. And furthermore, the onset potential is around 0.68 electron volt, 0.6 volt. So these dotted lines shows the corresponding profile of the platinum 100 layer, highlighting the platinum on the TiO2 terminated surfaces and achieve the comparably slightly improved performance as compared to the TiO2 terminated surfaces. So next we for a comparison and to make a good catalyst for methanol oxidation, this is the energy profile for SRO terminated system, and these blue, pink, and all these lines are similar as the previous slides. The main difference is that which is while the initial step is almost similar, which is first of all the CH bond will cleavage the CH3OH, and we will achieve the carbon dioxide at the end. So the main difference is that is the most stable intermediate is CO plus OH, rather than the carboxylic group in the previous slide, which is Ti2 terminated. So in this case, the overall potential is 1.17 electron, 1.17 volt, and the onset potential is calculated, which is 1.35 volt. So, which is substantially worse than the Ta2 terminated, and highlighting how the SRO terminating extensively stabilize the carbon monoxide and hinder the formation of the carbon dioxide. So to more explore these structures and how these carboxylic groups form and how they hinder the catalytic performance of the catalyst. So these are the transition state structure of the carboxylic COOH formation on the TiO2 terminators and SRO terminating systems. So in TiO2 terminating system, the OH group can detach from the platinum and approach to the absorbed carbon monoxide CO, and which relatively little geometric distortion we can see here. And in the case of SRO, the geometric distortion is too much as compared to the TiO system, which means that OH is most strongly stabilized on platinum and make platinum oxygen interaction, which makes significantly weaker before the CO bonding formation, and which leads to the much more strained transition geometry. Uh, And this figure, a visual demonstration is that the TiO2 terminating facilitate the carbon oxygen bonding formation, while the SRO terminating kinetically hinders it, and its overall potential observe the SRO supported catalysis. And to further in-depth analysis of this profile, we have calculated the energy along the reaction pathway. So this is for TI terminating system, and this is for SRO terminating systems. For TiO2 terminating system, the reaction process with the emitted activation energy barrier, which is around 0.93 electron volt, and is thermodynamically stable. As we can see here that the final at the end step, the energy become less than zero in or negative. So it means that the carboxylic COOH intermediate is more stable than the separated CO and OH, and the reverse barrier is high. So in the other case, in the case of SRO terminated system, we can see here that we need a 1.70 electron volt potential, and and this reaction is thermodynamically not favorable, and we can see here that all these energies are at the end are greater than zero and not negative. So in short, from these graphs, from these results, we can conclude that the TiO2 terminating promote both kinetically and thermodynamically stable, and favorable for the carbon oxygen bonding formation, whereas the SRO terminating strongly surpasses this step, which is so due to this comparison. This comparison provide an evidence that the much high over potential is required for the SRO based supported catalyst. And to the further study the metal interaction in these both systems. Uh, First of all, if we discuss about the SRO system, in SRO system, the oxygen, you can see here, these are the oxygen atoms. The oxygen atoms are make strong bonding with the palladium atoms and pulling some palladium atom towards them, and create a chemically non-equivalent PD sites. So in contrast, in the TI auto terminating system, this is little lower, and this make the less geometry distortion as compared to the SRO system. And due to this, the overall difference between the terminating strong modify the palladium electronic structure and geometry, which turn to the how the reaction intermediate bind the explain, and contrasting the catalytic behavior of a electrocatalyst for the methanol electrooxidations. So this is the just chart tendency difference. This is a comparison between TiO2 and SRO2 systems. We can, these yellow colors show the charge accumulation, and blue color show the depletion of the charges. We can see here that in the TiO system there is a accumulation of charges along the palladium atom as compared to the SRO based system. So by these charge density plots, we can conclude that in the PDs different substantially different polarization and induce the electronic potential, which provide a direct explanation for the different absorption certain and intermediate for the different catalytic performance observed in these two terminates. So as a conclusion, this brief study demonstrate how the performance of methanol oxidation catalyst reaction and the catalyst is strongly directed to the metal spot interaction, even when the active methanol surface remains structurally identical. So by comparing the palladium overlayer spotted different terminating of SRO2 system, TiO2 system, it is shown that the spotted induced electronic and geometric effect the strong influence on the stabilization, the reaction pathway, and the overall potential. So in particular system, the TA2 terminating promote the favorable CO bonding, and it's good for the catalyst for methanol. And this finding highlight the critical point for the rational sport of designing, and shows a promising method for the improving catalytic efficiency in the direct methanol fuel cells. So thank you, Marivan, for your time. If you have any question, you can ask me. And if you want to discuss in detail all this paper, all result of this paper, you can contact me via email.